What's up, 10C? This is the first part of 3 different videos I'm going to do here on domain and range, just to kind of try and break it down for you. A little bit of hard topic to understand and teach at a distance, but we'll do our best. So please, if you have any questions, fire me a remind message, email. We can set up a Google Meets, whatever works for you, okay? So this is the introduction to domain and range. First thing we got to do is sort through a little bit of terminology here. And the first one doesn't necessarily have to deal with domain and range, but it will kind of lead into that. And the first thing is discrete data. And so discrete data is when data values on a graph are not connected. Okay, so a graph of discrete data only shows the points as individual data points because the data cannot be broken down, because the data cannot be broken down. So it can't be broken into smaller and smaller pieces. And I'll talk about what that means here in a second. The difference, or the opposite of discrete data, is continuous data. And continuous, or what we may call non-discrete data values on a graph, are connected points. Okay, so a graph of continuous data is often what we just call like a continuous line. So if we look at these, this here is discrete data. There are these individual data points, and they are not connected by a line. While this one here, we could technically draw the same data points on this graph, but they're all connected by a line. And the reason for that is this, whatever data this is representing, can be broken into smaller and smaller chunks. So, there's technically something happening here, here. While with discrete data, it's only occurring at these exact points. And so, what does that mean? And how do we figure that out? So anytime I'm given a question or given a situation, I always ask, can we break the data down? So can we break the data down into smaller and smaller portions? If the answer to this question is no, you will have discrete data. Okay? And so things that we might graph that can't be broken into smaller and smaller parts are people. Even though you see a lot of graphs where it connects dots or connects them, technically you can't have half of a person. So when you're dealing with people or the number of items or the number of some sort of animal, you can't technically break those down into smaller and smaller portions. It's either one person or 2 people or 3 people. It can't be 1.75 people, right? You can't break that down into a smaller and smaller part. Well, if you say, can we break the data down, and you say yes to that question, we are looking at continuous data. And so what do I mean by continuous data? Well, things that can be broken down into smaller and smaller pieces are things like time. Right? I can have a minute, I can have an hour, I can have a second, I can have a millisecond, right? I can keep breaking those units down. Even money can be broken down, right? If you go to the gas station, it's 107.89, even though it's technically only $1.07 per liter, or whatever it may be, right? So money can be broken down into smaller and smaller pieces. Anything talking about weight or talking about distances, all of those can be broken down into smaller and smaller units. So let's take a look at an example. So how could you go to the store and buy cherries or apples or whatever it is, such that you would create a discrete data, or you could create a continuous data? So how could I buy cherries such that it would be discrete data? Well, I'm looking at comparing, the amount of money to something else here for both of these graphs. So this one could be a money versus the number of them, right? So one cherry, one cherry 50 cents, 2 cherries 20 cents, 3 cherries $1.50, whatever it is. Continuous could be money versus Continuous data could be like money versus, let's say, weight, right? So as I'm adding cherries, the weight's going to continue up. So that's how we can maybe, buy things in two different ways, or we could represent the data differently. So here is an example. So it says, in an environmental study in northern Alberta, Joe collected data on the number of different species of birds he saw in a 1 hour period every 2 hours for 24 hours. So he goes out and he's like listening to the bird calls and he records how many different he's hearing in 24 hours. Alice collected the temperature in the area after 2 hours for 24 hours. And then they plotted their data. So here's Joe's graph. It has the time and the species here. Here's Alice's graph. Here's the time and the temperature here. So then it says, does each graph represent a relation? Well, what's a relation? Well, a relationship is just like a comparison between two things. Do both of these graphs compare two things? Yeah. Next one. Are they both a function? Now you kind of have to go back to a previous lesson here and be like, well, what is a function? Well, a function is when we don't have repeating x or y values. So I could go do the vertical line test. Do both of these pass the vertical line test? Yeah. So they are both functions. And that's how I can tell. The next question is here is which of these graphs should be connected? So essentially saying which of these graphs could be considered discrete or which of these can be considered continuous data? Well, could I connect these points for time and the number of species? Well, time is continuous, right? Time can be broken down into smaller and smaller pieces, but species cannot, right? I can't have half of a species. So these data points would have to stay exactly as they are. I cannot connect them. This is discrete data. Let's check Alice's graph. So hers is time. Well, I can break time down into smaller and smaller sections. What about temperature? Could I have half of a degree? Yeah, I can have half of a degree. So technically, Alice could join all the points on her graph because this is continuous. Okay, and that terminology is going to come back up a little bit later once we examine what domain and range is. Some additional terminology we need to understand here is the difference between an independent and dependent variable. Now, if you talk about this in science, you should already have a good idea. But the independent variable is the variable for which the values are selected. And the value of the dependent variable depends on the independent variable. And we'll look at a few examples and kind of examine how we can figure out what is what. In terms of mathematically, the independent variable elements always belong to the x value. Independent always belongs to the x value, and that means dependent will always belong to the y value. Okay? If we express this as a table of values generally should always go like this, x and y. So the independent variable is x. That needs to be the left column on a table. Maybe it's not x and y, maybe it's the number of days I work and the amount of money I make. Okay? But regardless of what the situation is, whatever is in the left column is the independent variable. The dependent variable will then be in the right column. If I take these and look at them graphically, well, the dependent variable, if it's talking about x values, is going to be the x-axis. Or we could just say the horizontal axis. And the dependent variable is plotted along the y-axis. Or we could say the vertical axis. And the terminology matters because we're going to use these definitions to help us define domain and range here in a second. So let's go make sure we have a good understanding of independent, dependent before we start talking about domain and range. All right, so independent variable, that's going to be any of my x values. Okay? Dependent variable is my y value. Which means if we know this is x, that has to be the horizontal values of a graph. And dependent is going to be the vertical y values of a graph. if I gave you, let's just say, any old equation, a equals 4n plus 3, I should be able to look at this and say, well, what's the independent, what's the dependent? Really, I could look at this and say, well, usually equations are in the form y equals 4x plus 3. So that means n is the independent variable and a is the dependent, which is technically y. Okay? And we can say this side is the independent because I can select any number I want and just keep putting it into here. 4 times 1 plus 3, oh, that gives me 7. 4 times 4 is 16 plus 3 gives me 19, right? I can select these values and automatically have an outcome. And so whatever value I select here will change. And so this is dependent on whatever value I select. All right. So some terminology. Now, what we really got to get down to here in these lessons is talking about domain and range. And so domain, the domain of a relation is the set of all possible values of the independent variable. So all possible values of the independent variable. The range is all the set of possible values for the dependent variable. Variable. Okay, now independent, we said, is always looking at x. So really, the domain is all of the possible x values or all of the possible horizontal values of a graph. While the range is the dependent variable, so that's the y. Okay, so that's all of the possible vertical or y values of a particular relation or function. Now, how do I remember what's domain and what's range? Domain, I always say these are alphabetical. Domain and range are alphabetical. So domain is x and y is range because those are also alphabetical. That's how I remember the difference between domain and range. Okay, so terminology. On a graph, the values of the domain are plotted along the x-axis. So looking at this particular graph right here, they say, okay, here's this function or relation, and it goes from here to here. Well, what are all of the possible x values I could be on this graph? Well, they say the domain is between here and here. I can't technically have an x value for this graph right here. Like I can be like, oh, at -5, what's the y value? Well, the graph doesn't continue that far. So I have this domain being restricted between this area here and this area here on the x. The range is plotted along the y-axis. So looking at this, here's my function here. So this is the lowest value I could go on this graph up to right here, which is the highest value. So my range is all of the y values within that range or within that spread. Okay, so just a few notes here, and then we're going to go look at how I can figure out what domain and range is. So to determine the domain and range of a relation, we have to be able to correctly interpret a graph. Consider the graph here. And these dots are saying that the graph stops at that point. Now, can I change my pen color here? I don't really want to, does it? Okay, so looking at this, well, what is the farthest x value? I can't go this way. Well, I could follow this, and I keep going, and I keep going, and I keep going, and, well, right, this graph stops right here. Then I go this way. Well, how far can I go left? Well, I can go, left, 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 all the way to here. And then this graph stops. So my domain is just the numbers between these 2 points. I could be all of the x values between these 2 points for the domain. The range is how far I can go up and down on this graph. So how far up can I go? Well, if I follow this, the highest this graph can go is right here. So from here all the way down, well, the lowest this graph goes on the y is down to right here. So that would be the restrictions for my range. Some things to know is that we can also have those open and closed dots. And if you remember inequality notation, So I have a closed dot and I have an open dot. This means you can equal that number. If you remember inequalities from grade 9, this means you can equal that number, and this means you cannot equal that number. So if you have a solid line at the end of the graph like we do here, that means those data points needs to be included in whatever your domain and range are. If you have an open dot, that means that that point is not included in the data. So it means like included. I can't spell. So let's say I had this graph like this. Well, I could go all the way to 5 on the x, and then I keep going, and I keep going, and I keep going until I got to close to 3, but I would never be able to equal 3. I would get really, really close to it, but I could not equal 3 for that graph. All right, for the function shown here, if I'm looking at my x value, so if I follow this graph, you know, how far right can I go? I can go right all the way to right here. So I could go all the way to 3. And how far left can I go? Well, let's follow my line. How far left can I go? Well, it goes here. But really, this graph is just, because there's no dot at the end of it, we assume that it's just going to keep going. So it's going to keep going up and over, up and over, up and over forever. So that means it's just going to go this way forever and ever and ever and ever. Okay? So if you do not have a dot or an open-ended circle at the end of your graph, the graph will continues forever. Well, and how do we say forever mathematically? Continues infinitely. Skip that one. Okay, so now let's go back to talking about discrete data. Discrete data, if you remember, is just a whole bunch of individual data points. Now, when I look at this, this is a discrete data here. I can't say that, I beat every number from all the way here to here, because I don't have those data points being connected. So in order to express domain and range for discrete data, we will list them out. So for example, in this relation, how would I list out my domain? Well, the domain is all of the x values. And remember, the points always come in the form x comma y. So the domain for this would be 0, 1, 3, and 5. So 0, 1, 3, and 5. What's the range of this particular data set? Well, that would be just these y values. So 0, 5, and 7. I don't need to include the next 7 here because I already have it written down. We don't include repeats. Let's look at a problem-solving question. So Caitlin is marking the time for some music by clapping on the first beat of every bar. The table of values and the set of ordered pairs shows the relationship between the total number of beats and the total number of claps. Given the domain and range, use words and a list. So I want to list off, because I'm going to use a list here for my data because I cannot use interval or set notation because this is discrete data, right? Can I have quarter of a beat? Not really. So when I'm listing this, remember, this is my independent and this is my dependent. So the domain, I literally just write all these down. 1, 5, 9, 13, 17, 21, 25, 29. Done. Do the same thing for the y. Well, the y is just these whole numbers. Because I can't have half of a clap, I literally just have to list them off. 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's how I just write domain and range for discrete data. Literally just list them all out. Now we need to look at how can I do the same thing for continuous data. Now continuous data is much more complicated. So let's go take a look. So they give me this relation here, and they say, well, just describe in words the domain here. So I'm going to start that off. Domain is all real numbers, okay? Anytime we have continuous data, this right here is telling us this is a continuous line. So I always start off with that if I have a continuous data. So domain is all real numbers, and then I can talk about my parameters from there. So looking at this graph, how far right can I go? Well, I can go right all the way up to here. So all the way up to 3. Can I equal 3? Well, I can't equal 3 because this is an open dot here. So I can't equal 3. I'm just going to write that for myself. Then, I can keep following and following and following and following all the way up to here. So that's at -4. So this, for the x value, I could be any number in between here. And can I equal -4? Yeah, because that's a closed dot. So when I'm going to express that in words, I say the domain is all real numbers between -4 and 3. So I can be from -4 to 3, but I cannot equal 3. So I'm going to say not including 3. Not including 3. So there's my domain of that graph. Now I want to go to do the same thing for the range. So I want to go look at the y values, like how far up can I go and how far down can I go? Well, how far up can I go? Can I be a value way up here? No, because the graph stops right here. So how far up this way can I go? Well, all the way to 4 on the range. That's the highest value I can be on the range. And that was an open dot, so I can't equal 4. How far down can I go then? I can go down all the way to this point right here on the y, which is at -5. And I can equal that number. So my range, I could be any value within that part, right? Because I could have a y value at, -3.5, comma, whatever this is, 3. Now to express that in words, I say the range is all real numbers between, well, the lowest number I could be is -5, and 4 is the highest x value, or sorry, the highest I could be on the y, and I can't equal that 4, so I need to say that, not including 4. Okay, let's look at another one. So here is this. This is actually an absolute value function, not that that matters. So describe this in words. So I want to talk about the domain. So I always start off with that. Domain is all real numbers because this is a continuous line, so I can say that. All real numbers. That's saying it could be any tiny little value within this range. So how far to the right can I go on this graph? Like how far this way can I go over? Well, this has an arrow. So technically this line is going to go up and over, up and over, up and over forever. So I'm going to go all the way this way. Right? I can go this way for infinitely far if I want to. What about how far left can I go? Well, let's see. How far left can I go? Well, this graph, again, it looks like you can just keep going up and over, up and over, and up and over, forever and ever and ever. So how far that way can I go? Well, I could go all the way to -infinity if I wanted to. Now, we don't need to say that. Me saying domain is all real numbers, that's satisfied. Domain is all real numbers, any number you can possibly think of, that's part of my domain. And so that's all I need to say for the domain here. Now I'm going to look at my range. So my range. What's the furthest down I can go? Well, can I be a number down here at like -10 for this graph? No, because the red line stops right here. And it looks like it kind of comes and it bounces off. So whenever it bounces off, we're going to say right here, that's 0. If it bounces off a number, we're going to assume, unless they tell us otherwise, you can equal that number. So the lowest we can be here is 0. And now, because we said this graph goes up and over forever, this is just going to go this way. The graph could be, the range can be all numbers greater than 0. Excuse me. So I just need to write that. The range is all real numbers greater than 0. I guess I should say greater than, let's say, or equal to. I just say greater than, that means it's not, I be greater than 0, but if I can be greater than or equal to, greater than or equal to means it comes down, it touches 0, and then it goes back up the other way, which is what's happening in this example. Okay, one more example here. If you want to pause the video and maybe write down what you think the domain and range is in words, I would suggest doing that if you feel comfortable, and then checking your answer with what I'm about to do here. So the domain is talking about all of the possible x values. So how far right can I go? Well, the domain is, see, this graph keeps going over and over and over. So where does it stop? Like, how far right can I go? Well, this graph has an arrow saying it goes over this way. So how far right can I go? I can go right forever, because this graph is going up and over, up and over, up and over, forever and ever and ever. So I can go technically to infinitely high to the right. How far can I come to the left? Well, can I go all the way this way? No, because I don't know if I can erase that. No, because the graph stops with an open dot right here. So how far left can I come? I got to stop right here at -2. Now, when I talk about that in words, I always start off with domain is all real numbers, because this is a continuous line. Domain is all real numbers. What am I compared to -2? I'm -2 and this way. So am I greater than -2 or am I less than -2? Well, I am greater, because I can be all these positive numbers up here. So the domain is all real numbers greater than. Now I could add or equal to here, but technically I cannot go equal -2. I could equal 1.999, or sorry, -1.99999, but I can never equal -2 because of this open dot here. So the domain is all real numbers greater than -2. And I'm done. The range, let's do the same thing with the range. Well, how far down can I come on this graph? Can I go down forever? No, because once again, once you go down all the way to here, you can't go down any further on this line. So that's restricted by this point of -3. Now this graph goes up, and we said it goes up and over forever, which means the range will also just be able to go 3 and up. Now I need to express that in my words. So the range, because it's a continuous line, is all real numbers. Now, am I greater than -3 or am I less than -3? I am greater, because I can be these positive numbers this way. So the range is all real numbers greater than -3. I can't equal -3 again down here because it's an open dot. Okay. So I have this Desmos activity that I want you to try. I've used Desmos a little bit before, but I'm hoping this might give us a little bit more hands-on visual representation of domain and range. So please try this activity. It's not for marks, but it is for you to practice and for me to see if you have understand based off of my video and notes. So please give this activity a try. Fire me a message if you need any help. Okay, guys, thanks for listening. Have a good one.